In section 4.1, we're going to be looking at exponential functions. And so let's just kind of jump in here and look at a couple of formulas and kind of explain where everything is. So an exponential function is an exponential growth or decay function that grows or shrinks at a constant percent growth rate. So what you want to know is, here is the two formulas that you need. Now this says the first formula or the second one, because you'll notice they made a substitution. Instead of putting a 1 plus r here, they've changed it to b. And I'm going to show you how both of those work out and what you need to use depending on the situation. But let's first define our variables. So a is going to be your initial value. A is going to be your initial or starting value. It may be the starting on the population they give you. It might be a certain substance that you're starting with and it's decaying. R is going to be your percent growth or decay rate. And this is important to note that it is as a decimal. So if it's given as a percentage, you need to change that to a decimal before you get going. And then B is your growth factor or growth multiplier, and it's typically going to be positive. And so I just want to kind of jump right in. The best way for us to look at this is to look at given situations and then see how we can pull the data from there. And so it says India's population of 1.14 billion in the year 2008 had a percent growth rate of 1.34%. Write an exponential function for India's population and use it to predict the population in 2020. So let's pull out some pertinent information here. So first of all, we know that in 2008, we had 1.14 billion. We have a growth rate of 1.34%. And we want to predict the population in 2020. The key that sets me off to show me how to set this up is it says write an exponential function. So let's see what we can do with this. So I am going to be working with this equation here. F of t is equal to a, parentheses 1 plus r to the t. We're going to figure out if we can pull in the information we need. Now, as you've seen in previous problems, typically we don't ever use the year 2008 or 2020. Math people are lazy. We want to simplify things down and we want to use much smaller numbers. And so let's pull that data first. So we know that in the year 2008 that we had 1.14 billion. And so since this is our starting year, we're going to call this to be t equal to 0. And so then any year that we base it off from there, this is our zeroing year. And you see this very, very often in problems when you're dealing with years as values. Since we are starting with 1.14, that is our initial amount. That means A is going to be equal to 1.14. Since our growth rate is 1.34%, then my rate is going to be 1.34%. But we've already mentioned this is always written as a decimal. So I'm just going to change that to a decimal by moving it 2 places to the left. So 0.0134 will be my R. And it says use this to predict the population in 2020. So what we're trying to figure out is in 2020, notice that is 12 years difference from 2008, so that's t equal to 12. We want to figure out what is the population. And so let's set it up. We've got f of t equal to our initial value 1.14, parentheses 1 plus our rate 0.0134 raised to the t. So this first part here that said write the exponential function, that right there is writing your exponential function. And in the homework, I would go ahead and hit submit if they have that blank there and make sure you have gotten that correctly before moving on to the next blank. For the next one, we want to predict the population in 2020. Well, we've already changed that to a t value of 12. So now we're just going to do f of 12 equal to 1.14 times 1 plus 0.0134 raised to the 12. Now just be careful when you go to plug this in your calculator. I would do as minimal steps as possible in my calculator. I would go ahead and add that, so that gives me 1.0134 to the 12th. And then when you enter that in your calculator, you're going to enter 1.14 parentheses 1.0134 raised to the 12th and hit enter. And that will give you a value of 1.337 billion. And this was a prediction of the population in 2020. And I actually pulled up the population of India just the other day because I was working this problem in college algebra as well. And I was wondering, like, I wonder if this is accurate of whenever they wrote this problem, if, you know, this is actual. And it was really close to the number. And so that was really interesting. So with this, to summarize, you want to make sure you pull your data, convert your data if need be, such as your rate to a decimal, and then create a function and then evaluate that function. So this is one example, and I like to do this one because it has population in there, and those years typically throw students off because they use the 2008 and 2020. Let's go to the next one, and let's look at a decay function. Now in the decay function, it says bismuth-210 is an isotope that radioactively decays by about 13% each day, meaning 13% of the remaining bismuth-210 transforms into another atom. And in this case, that polonium-210. If you begin with 100 milligrams of bismuth-210, how much remains after 1 week? So let's pull our pertinent information that we know. First of all, we are starting with 100 milligrams. So that right there is going to be your initial value of 100 milligrams. And then you see that you have a rate of it's decaying by 13% each day. So my rate is going to be equal to negative 13% because it's decaying. And so that would be negative 0.13 because you always wanted to convert it to a decimal. And then it says if you begin, let's see, it is 13% each day. And so if you begin with 100 milligrams, how much remains after 1 week? Well, since our rate is in terms of days, our time we're going to make in terms of days. So we're going to say how much is left after 7 days. And so use your similar equation. We're going to use that f of t equal to a parentheses. And in this case, we're going to do 1 plus r to the t, but you're going to see a negative come out of there because of our negative rate. So this is going to be equal to 100 times 1 minus 0.13 to the 7 or to the t to get our function. And so our final function would be 100 times 0.87 to the t. So there's your function we've created. So with this one's a little bit different because it is decaying, our rate is negative. So that's where this negative came from. And then it says find it after 1 week. So we would say f of 7 is equal to 100.87 to the 7th. And when you type all that in, you want to type that in your calculator just like that, just like what we saw up here. And this gives you approximately 37.726 milligrams. Now the good thing about these types of problems is you can see, does this make sense? Okay, I have 100 milligrams of that. It's decreasing. I got a value of 37. Well, that makes sense. If we had gotten a value of 370, I would look at it and go, that doesn't really make sense that I'm decaying, but I now have more of that product. And so my hope is that as we work through these problems, like you can see where the data is coming from, how you're plugging in the formula, and help to kind of ease yourself through this exponential function section. Let's do another one. Let's look at this example here. And with this example, we're going to look at, again, another kind of population one, but now we're going to be looking at a population of something else. With this one, we're going to look at the population of deer. And it says in 2009, 80 deer were reintroduced into a wildlife refuge area from which the population has previously been hunted to elimination. By 2015, the population had grown to 180 deer. If this population grows exponentially, find a formula for the function. And so for this one, we need to create a little bit more of what's going on. So we're going to pull our data first. And so we see that in 2009, there were 80 deer. And we see that in 2015, there was 180 deer. So let's kind of relate that. So in 2009, that's going to be our starting year. So we're going to call that t equal to 0. And so if I wanted to create 2 points from that, I could say, well, that's 0, 80, working with the population and the y value. And then we say, okay, well, in 2015, well, let's see, that's going to be 6 years later, so that means t equal to 6. So then we're looking at the pair of 6, 180, just pairing up our time with our population. So for this one, we don't know. We just know that it grows exponentially. We don't know the rate. So this will be the one that you want to start with, and you want to make 2 points. And we're going to use that other function of f of t equal to a times b to the t. And again, the reason I'm using that one is I know it grows exponentially, and that's an exponential function, but I do not know the growth rate like on the previous one. And so I'm going to use the first piece of data. I'm going to say f of t is equal to. Now remember, this a right here is your initial value, and we are initially starting with 80 deer. And so I'm going to say 80 b to the t. Then I'm going to use that initial value to create somewhat of a function. I'm going to now take this second point and plug it in to figure out other pieces of this. So let's see, 180 would go here in y equal to 80 times b to the t, which is 6. So I use my first piece of data to set the initial. I use my second piece of data to fill in 2 more variables. And now I can solve for that b value. So I'm going to divide by 80. So it gives me b to the 6 equal to 180 divided by 80. That's 9/4. And then to get rid of this 6th power, I'm going to 6th root it. And I'm going to use my calculator to help me with that. And so this gives me b to be approximately 1.1447. And so now I can rewrite this function and say, well, then that is f of t equal to 80 that we already knew, 1.1447 to the t. And then remember on that previous page, we said b was equal to 1 plus our rate. Well, I could split that apart. If I subtract 1 from that b value, that gives me 80 equal to 1 plus 0.1447 to the t. So now you can see that 0.1447 was the rate that's coming from it. So either of these 2 functions would work for figuring out a formula for the deer population. And so again, if I've kind of lost you a little bit, just kind of pause, backtrack to the beginning, and listen to it again. Your battery's not running low. That was mine real quick. Always tell my students to plug in, make sure your battery's charged before you take your test. Same goes to me. Plug in, make sure your battery's charged before you record a lecture. Let's look at example 4. Now in example 4, this one doesn't give us an initial amount. So we're going to have to do a little bit more legwork for this. So if you don't print the notes beforehand and you're taking notes in your notebook, I would go ahead and make sure you have some room for it, because we're going to have to do a little bit more work because we have a little bit less data. So for this one, I've picked a problem that is just not necessarily population or had a lot of words to it. It just had some numbers, because I'm going to show you how this works out. So this says, find a formula for an exponential function passing through the points -2, 6 and 2, 1. So we're not in college algebra anymore. We're not looking for just slope and create those 2 points. So we're going to have to approach this a little bit differently. So here's what we're going to do, and it's going to be a little bit similar to the previous problem. And let's kind of write some steps as we go to help us and also give you a good guide when you go to do this on your own again. So 1, you want to write 2 equations based off your information. So in our information, we've got -2, 6. And so this is going to be our t values, and this is going to be our f of t values. A and b is what we are trying to find. So I'm going to be working with f of t equal to a b to the t. A and b are numbers. We just got to figure them out. So I'm going to plug in what I know, and I'm going to say, okay, in that first one, I'm going to have 6 equal to ab to the -2. The second equation I'm going to write is going to use the 2, 1. So that would be 1 equal to ab to the second power. Now that I have two equations, step 2, I'm going to solve one equation. Sorry about that jump. I guess my computer is not liking me today. So step 2, I'm going to solve one equation. And so I'm going to solve one equation. I'm actually going to solve it for A. And so I'm going to take that first equation, 6 equal to AB to the negative 2, and I'm going to solve it for A. So this is A times B to the negative 2, so I'm going to divide both sides by B to the negative 2. So that gives me 6 over B to the negative 2 equal to A. And if you remember your properties of exponents, having a negative 2 in the bottom, I can bring it up and it makes it positive. So now I have 6b squared equal to A. After you get one of your equations solved for a letter, step 3, you want to substitute into the other equation. So I'm going to substitute into the other equation. And so I'm going to take 1 equal to something b squared, and that something I'm going to plug in is this piece right here. And I'm plugging that in for that A that we had. And so I'm going to say 6b squared. So it gives me 1 equal to 6b to the 4th. Remember properties of exponents. And then now I only have one letter in the problem and I can solve for b. And so I'm going to divide both sides by 6. So it gives me 1/6 equal to b to the 4th. And then I'm going to 4th root both sides. So the 4th root of 1/6 is 0.6389, and that's going to be our b value. Now that we have one of those letters, step 4, we are going to plug b into, we're going to plug b in to find A. And so I would say, okay, well, let's look at this. We know that right here, this piece, that A was equal to 6b squared. And so I'm going to say A is equal to 6 times my value squared. And now I have that value, 0.6389, retained in my calculator. So I'm going to square it, multiply it by 6, follow order of operations. And so it gives me A to be approximately 2.4492. And so now that I have my A value and my B value, I can go back and create this equation. And so I'm going to say step 5, I'm going to plug A and B into the equation. And let's write that out. So that would give me f of t equal to 2.4492 times 0.6389 to the t. And so then that would be my exponential function for those two values. And so this is more difficult. I mean, we're almost halfway through pre-cal. We're beyond just finding slope and intercepts, but I want to kind of go slow and walk you through this without deer or decay or population, so you can kind of see how those pieces are working out. So we have now been able to work at problems and set them up, find initial values, find growth rates, and then even create some exponential functions. So let's continue our conversation of these exponential functions, and let's look what kind of is going on from a graph and see if we were given information differently, if we could work it out from there. This example is worded a little bit differently, so I want to expose you to this and help you with this, but it's going to be a rinse and repeat and work with what we've already been doing. And so it says find an equation for the exponential function graphed. Okay, well, you're going to approach it the same way as you did in example 4, but I want to get you going with it and kind of set you up for success here. So when you're looking at this one, the same thing is going to be true as what we did in the previous one, But first, you're going to have to find your 2 points. And so I like to look for 2 really good points. When I say really good points, I want to look for where the blue line is crossing a grid point. And so I see a really good point right here. And so this would be at the point -1, 1. And then let's see, I see another really good point like right here. And so 1, 2. And so then what you're going to do is you're going to use those 2 ordered pairs, just like what we did in example 4. So you're going to do this the same as previous. And so that would be a really good example for you to now try what we just did, follow those 5 steps, and see if you can create that exponential function. But I want to show you a different way that the data can be presented. Now, with all this talk of exponential functions, what kind of math teacher would I be if I didn't talk about some compound interest? And I really like compound interest problems because I feel like it's some of the most applicable stuff we do, especially because you're moving on and you're in college and you're in a pre-cal class. And so you're working towards some kind of goal or career. And so your goal is to be self-sufficient, to have a job one day and take care of yourself or a family. Well, in doing that, you're probably going to make some big purchases. You're probably going to purchase something like a car. That's always kind of the bigger purchase, or maybe a home one day. That would be wonderful. Well, in that case, I feel like we need to have a talk about interest. If you can't understand interest and what it does and how it can be accumulated, then I feel like it's not going to help you to be financially successful, because there are really great commercials out there and ads that talk about like 0% for this, or we're going to finance for so long. But I want you to understand the ins and outs, because when you're talking about interest or payments on purchasing things such as a car, it doesn't come down to just how much is the monthly payment. It comes down to how much interest. And at the end of the day, how much money are you going to be paying this for the life of the car or the life of that loan? I mean, better situations would be that you're investing money, but I feel like purchasing the car information is a good conversation to have. And so this leads us into working with compound interest. And compound interest is a formula such as this: A of t equal to A lowercase, time parentheses 1 plus r over n to the nt. And let's just kind of identify our variables here. So A of t is going to be your account value. T is your time, and it's crucial that you have that in years. They're going to try and trick you and give you something that's not in years, like months, weeks, or days. Make sure you convert that to years. A is your initial amount. It's considered your principal. It's the amount you borrow or invest. So if you're investing in something, that's your lowercase a, your initial amount. If you're purchasing, such as a car or a home, that would be your initial, like your purchase. R is your annual percentage rate. This always needs to be written as a decimal, just like what we did in previous problems, so make sure of that. And N is the number of compounding periods in 1 year. So let's have a conversation about that. If it says that is compounded annually, well, that's going to be equal to N being 1. If it says semi-annually, such as a sale that a lot of stores will have, that would be twice a year. If it says quarterly, just like 4 quarters are in $1, then that would be 4 times a year, or the quarterly report, say for a business. If it says weekly, you want to think about how many weeks are in a year. That would be 52. If it says daily, that would be 365. And if it says monthly, that's going to be 12. And so let's look at this first example and see if we can plug and play and see what we can do with this. So it says if you invest $3,000 in an investment account paying 3% interest compounded quarterly, how much will the account be worth in 10 years? So here's my best advice for working some of these. First, write your formula. You probably heard me say that before. Second, identify all your variables. And so if you invest $3,000, and so that is the amount that's my initial amount. So I'm going to say A is equal to 3,000. And this is the amount that you invest or borrow, your initial amount. It is an account paying 3%. And so that's going to be my R. Now 3%, you always need to move that decimal, and we're going to use it as 0.03. It says that it's compounded quarterly. And so just what we previously wrote, that means our n is going to be equal to 4. And how much will the account be worth in 10 years? So t is going to be equal to 10. So now that I've identified all my variables, I am going to plug in to my formula what I'm working with. So I'm going to plug in everything I know. So this will give me A of t, the amount I'm trying to find, the account value, my initial 3,000 times 1 plus my rate, which is 0.03 over 4 my n. 4 is my n and t is 10. Now don't just run to your calculator and plug all that in. Do as much arithmetic as you can before you run to your calculator. And so let's see, that would be 1 plus 4 times 10 would be me 40. I'm going to take that 0.03 and I'm going to divide it by 4. So let's see, 0.03 divided by 4, that gives me 0.0075. So that would be 3,000, 1.0075 to the 40th. Now you can run to your calculator and type that in, and that will give you an overall value of 4,045.05. And so not too bad, especially compared to the previous examples, but I wanted to walk through on using your formula and plugging in all of your values. Another type of interest we're going to look at is the compounding continuously interest. You're going to notice a new little part in this one. This is the formula that uses your e to the x. And this is when time between compounding here periods has become very small. And so we talk about compounding continuously, not such as the daily or weekly or quarterly like you've seen in other problems. So let's kind of review these two. And so we can see that f of t is equal to a times e to the rt, or you have typically referred to this as PERT, PE to the RT. But I just want to emphasize here that whether it's P or A, this is still your starting amount. So you're still seeing that multiplier times your initial value or starting amount. And so I want to relate this to things that you've seen before, such as the PERT, your principal e to the RT, but also to what we've been doing in this lesson of that A being your initial value. R is still your continuous growth rate. Remember that needs to be written as a decimal. And T is your time. And so it says if $1,000 is invested in an account earning 10% compounded continuously, there's your keyword right there, continuously, find the value after 1 year. So the first thing I'm going to do is I'm going to write my equation. So I'm going to say f of t is equal to AE to the RT. I'm going to identify my variables. So it says 1,000 is invested, so that's my A. In an account earning 10%, so that's my rate. I'm going to change that to a decimal, so 0.10. Compound it continuously, that's where I got that I want to use this form. Find the value after 1 year, so my t is going to be equal to 1. I'm going to plug in everything I know, so that gives me 1,000 e to the 0.10 times 1. Then I'm going to use my calculator to assist me with that, and this gives me the value of 1,105.17. So you can see working with this equation, it's still similar processes. Write your formula, identify your variables, plug them in, do as much arithmetic as you can before you run to your calculator. So I would not have written this in my calculator with 0.1 with a parentheses and a 1, because that's where mistakes happen. You want to enter in your calculator 1,000 E, and then it'll do the house stop sign, and then it'll be 0.10, because 0.10 times 1 is just 0.10. So be very minimal with what you're typing in as you're calculating it, and that will help little mistakes not to occur. Let's look at another example here. Last example here for this section. It says radon 222 decays at a continuous rate of 17.3% per day. How much will 100 milligrams of radon 222 decay in 3 days? And so you can see that signing some keywords we want to see. It decays at a continuous, we've got a rate, we've got an amount, and we've got a time. And so let's work with this. This would be f of t is equal to AE to the RT, and I knew that it was going to be E from the fact that it's continuous. My rate is 17.3%. Since it's decaying, I want a negative, and I want to change that to a decimal, 0.173. Then I know that my initial amount is 100 and my time is 3 days. And so I'm going to say, okay, my initial amount is 100 e to the, my array is 0.173 times t, which is 3. I would, and don't forget our negative because it's decaying, I would plug this part into your calculator and get that value, and then do 100 e to that value, and you're going to get approximately 59.512. And then see if your answer makes sense. We started with 100 milligrams, and so if we are decaying, we should have a less amount. If you got a really large amount, then you will know, like, okay, maybe I need to go back and check something. You know, maybe you forgot this negative that it's decaying. So I hope this helps. Please contact me if you have any questions, comments, or concerns.